Hello and welcome back to part 2 of this new tutorial series of the OptiCore add-on for Blender. In this part, we will be looking in detail at the feature to load a complete lens design from a ZMX file. This includes some sources on the internet where you can get such files, and then to look through a few different optical designs to show what can be done, and also some example of what is not supported at the moment. This tutorial is quite long because I cover several different optical designs and for some of them go into great detail about some particularities that these designs feature. So if you're interested only in something specific, then make sure to check out the chapter markings in the description below, which allow you to jump there directly. As a reminder, you find the feature under Add, Mesh in the OptiCore Optics menu. And setting up for this presentation, I've already pre-selected a design file for a wide-angle lens, which looks like this, and as you can see has quite many elements, 13 to be precise, plus of course an aperture. So the first thing you might notice when just looking at this model as it's generated by default is that the model is rather rough. You can clearly see the segmentation on the outer edges of particularly the big lens in this case, and that is not so surprising because by default the resolution parameters here in radial and angular direction are 8 and 16. In comparison, for the normal lens feature of OptiCore, where you only generate a single lens at the time, the default values are 32 and 64, so significantly higher in resolution. If I just add these, then you can see that now the mesh looks pretty smooth, barely visible in this view that the edges are still segmented. But I've chosen for the load from zmx file to use much lower default values, and this is for performance reasons. So for a single lens, it doesn't matter so much. However, if you import something like 13 lenses, as we have in this example, the whole performance can be much lower with the higher resolution of the mesh, because due to the way Blender works with these kinds of operators here that I use, every time we change any value, and this could be the number of rays in the internal ray tracing feature, which doesn't affect the meshes at all. Still, each time all the meshes are regenerated from fresh. So if we have 13 meshes at a high resolution, this can lead to quite a significant processing time, maybe half a second, which would be noticeable in the performance when looking at ray tracing, which has nothing to do with the meshes. So for doing this, for looking at the lens in a cross-section model, adding a ray fan, the larger number of rays, and looking at the focus like we do here, the resolution of the meshes isn't important at all, because this internal sequential ray tracer independently traces to the precise curvature of the surfaces, the non-segmented surfaces. So whether you have a really high resolution or a really low resolution, the intersection points of the sequential ray tracer are exactly the same and are not impacted by this in any way. So for doing this, it's absolutely fine to have a low resolution mesh, and then only when you're done playing around and want to bake the mesh for use with, for example, cycles, you can increase the resolution and be done. Another performance critical feature, if we go back to adding a ray fan and let's say we generate the mesh with a high resolution, and because we want to look at the uninterrupted rays with very high resolution fan, let's take something even higher, 15,000 rays, you can already see that the whole thing takes quite a while. If I now generate a beam at 5-degree angle, you can see that on my computer it took a few seconds to generate everything. So For example, what could happen, you accidentally double type and type a much too large number in here. I'm not going to do this right now. Then, yeah, your performance will be really bad and you'll have to wait many seconds for this to finish. So if you ever end up in a situation like this by accident and you want to revert this, there is a simple feature for this as well. So just delete everything. And now in OptiCore Optics, we have this option to reset performance critical settings. If I just click this is basically instantaneous. And now go back to loading the lens from the zmx file. Then the mesh number of vertices of the mesh, as well as the number of rays in our ray fan, have been reset so that we're back to a good performing solution. All the other settings are unchanged, as you can see, for example, from the file name still being selected as before. Okay, so this just as a quick introduction to the kind of systems we will look at, and the first aspects to notice about resolution and performance. Now the question is, where did I get this specific file for a wide-angle lens? And the answer to that is a database on the internet that I found and wanted to highlight here. The site is called lensdesigns.com and it collects lens designs from different sources. A lot of them from patents, but also from textbooks. And these design files have been prepared and submitted by different people, which are always listed in kind of blog posts on this page. A word of caution at this point, before we go into any detail, please make sure to check copyright restrictions for each of these designs if you want to use them for an actual project. So, for example, the site has lenses from patents that are still active and not just expired patents. And designs from textbook might have their own copyright restrictions, so please make sure to check this yourself for each design that you want to use more than just for exploring for yourself, for example. So yeah, this page collects lens designs, many of them in the zmx format, also in other formats, but many in this zmx format, and it groups them into different design types. So for example, there are photographic primes, so lenses with a fixed focal length. Then there are zoom lenses, eyepieces, telescope, projector lenses, and microscope objectives. So for example, if we go to the primes page, well, there are some text as well here. Whenever new lenses have been added, there's quite a lot of description here that might be interesting to read with some pictures shown. And then if we scroll either to the bottom of this page or on the downloading page, there's both a table with summary of the designs and link to a Google Docs folder where you can get all these files. So you could download all of them. It's German here since I'm from Germany, so you can download everything at once. And okay, it doesn't load quickly on the Google Drive, but there's also the summary Excel sheet with a little more description available. So yeah, most of these files, for example, this CN some number, this would be a patent number. So if you want to know if this patent is expired or not, or download the patent in original, you might be lucky and find this on Google Patents if you search for the number. Okay, so yeah, I've downloaded these lenses from lensdesigns.com, and it's one of those files from the photographic primes from which I got this design that I showed here. And besides complex lens systems like this one, you can also look for sources of simpler lenses. For example, simple achromatic doublets or triplets are widely available from off-the-shelf optics manufacturers. There are several companies that sell lenses of this type for laboratory purposes. Two big companies with a very wide variety are Edmond Optics and Thor Labs. On their respective websites, you can look in the category of optics and then optical lenses, where they have quite a number of further subcategories. For example, achromatic lenses, and where then is even a further variety with different coatings and optimizations for different wavelength ranges. For the purposes of using them in Blender for rendering, you don't need to care about the coatings at the present, because setting up any color effects that this would be associated with is a matter of setting up the cycles shaders and not within the current scope of OptiCore. Anyways, you have a wide variety of lenses where you can choose by focal length and size. And if you open up the menu for one of the items, you will find the zmx files that you can download. These off-the-shelf suppliers also sell complex lens systems, i.e. complete objectives. However, the optical designs of these is usually not published, so you can't expect to find zmx files for those. But still, this is a great resource as well for learning about the design of singlet, doublet or triplet lens groups. Back in Blender, we can now go through a few lens designs and see what we can do and learn about them. I've again loaded the wide angle lens shown earlier with default settings here. So I will activate the ray fan with cross-section view, increase the number of rays so that we get a good amount of rays passing through the lens. That's probably more than we need. With the 2D fan, and we will display only the uninterrupted rays for now. So ray fan is set up. Let's go into side view and start increasing the fan angle to see what's happening for this wide angle lens. Okay, so it's quite wide angle, so we can increase the angle beyond 30 degrees, approaching 40 degrees. And now we see that suddenly the beam gets cut off if it was vignetted at around, just over around 43 degrees. And it seems to be cut off from the top direction in this view. However, if we zoom in a bit and take a bit closer look where the vignetting is happening, we can see that at every surface, the ray fan passes well within the boundary of the optical surface and also well within the aperture itself. So doesn't really seem like the vignetting is real here, and indeed it is not. This is actually because in my first implementation of how this ray fan is initialized, that is working here, this implementation is not great for large off-axis angle and doesn't cover the full lens in a case like this. Until I have a better and more general method available, there's a little workaround now. So to highlight how this works, I'm gonna display the entire initial ray fan, and you can see here that our rays come from the very edge of it. And now there is this fan diameter factor, which here we can just set to 3 to oversize the initial ray fan. Some bug rays here actually, which we don't need to worry about because they do not trace to further surfaces. But you see that now the initial lens is fully covered. And if we go back to display only the uninterrupted rays, then we can see that the ray fan now again fills the entire aperture, so is not falsely vignetted at this point. So yeah, until a better and more general implementation is available, this is the workaround that you can use for large angles, and so we can keep increasing the angle further. So with this lens we can pass 50 degrees. And finally we get some real vignetting around 55 degrees. And at close to 57 degrees we get full vignetting and the lens doesn't transmit any rays at all anymore. So we have learned that the absolute maximum image circle of this lens is around 57 degrees. However, for a lens like this, which is not a fisheye, it is quite unlikely that the manufacturer really has designed it to be used this far out. In a zmx file, there can be an indication of either maximum field of view or indirectly via the image size. And this file does specify an image size of 21.6 millimeter, which happens to be the diagonal of a 4/3 type sensor. So that makes sense. For a non-fisheye lens, as I said, this one is, we can then assume so-called f10 theta projection, which means that the distance of the focus spot, if I add a few more rays to really highlight the focus spot, so the distance of the focus spot laterally from the optical axis is the product of the focal length times the tangent of the image angle. Together with the effective focal length of 50.3 millimeters in this case that OptiCore calculates here, you can actually enter this as an equation into the Blender UI, which is a really nice feature. So we go into the fan angle, and now we want the arctan of 21.6 divided by 2, because that's the diameter. Here we want the radial distance, so we take half of that and divide that further by the focal length, 15.3. And that gives me an error. Was it? Yeah, it was A10, but also A10 returns the value in radians, not in degrees. So we need to convert this by multiplying by 180 degrees and dividing by pi, which I'll just do approximately here. And so as a result, we get a maximum angle of 35.2 degrees. We can double check this calculation forward by now looking at the vertex position. So I'll just pick one of the vertices in the focus spot here, and we get a Z coordinate of 10.4. And we would expect 10.8, which is half of the 21.6. However, when the lens has some distortion, as you can expect for any real lens, you would also expect a deviation from this f10 theta relationship, and this is exactly what is happening here. Okay, moving on to the next feature to visualize the performance. Now, so far I have shown only a single angle at any time, and I have to delete this and reload the operator to get the controls back. So I will reset this to 0. And now if we're interested in displaying multiple angles at the same time, there is this field below the fan angle selector here, which is just labeled additional because the text is cut off, but that's short for additional angles. And here we can enter a list of decimal values separated by semicolon. So for this lens, for example, we could do 10 degrees, 20 degrees, and 35 degrees. And if I hit enter, then you can see we now get 4 beams in total. Only the primary angle, which is this one selected by this field, is then selected in the edit mode view. This I did because I found that selecting all fans at a time can lead to a visual mess, and so I found this more informative at the end. Now with multiple angles, we can zoom into the focus plane, and by default the focus for each ray fan is, or the ray fan is traced to the nominal image plane. So all the ray fans end at the same distance along the optical axis, but we can now activate the RMS focus option, which will individually for each beam calculate the best focus position according to the root mean square difference from the average of all the rays. And yeah, this works for each fan angle individually. so you can see if there is a field curvature in the image. For this lens, we actually can see that there is some back focus increase for higher field angles. So when you set this lens up for use with cycles, for example, so for rendering in Blender, you might want to set your image plane somewhere along the middle of this, or if you want to focus at the center, or if you want to focus at the outer edge, you're gonna have to set your sensor a little differently. Now, however, a word of caution with this example. Here so far, I've only shown a 2D ray fan. However, 2D ray fan is not really accurate for calculating the RMS focus, particularly when you're looking at off-axis angles. Then you would need one of the 3D ray fan options. However, I'm not going to demonstrate this with this lens, because if we display the entire ray fan here, you can see that only a very small fraction of the initial ray fan actually passes through the lens and makes it to the image sensor, which again is one of these deficiencies with my current implementation, and needs to be solved by a better implementation in the future. And this is already very inefficient with a 2D ray fan for a wide angle lens like this, and with a 3D ray fan even more so. And so this would just be too computationally intense for this tutorial video. Instead, I'm going to skip demonstrating this for this particular lens, and I will show it with the next example, which is more efficient because it's not such a wide angle lens. Back to the default view, let me select the next example, which is another prime lens. Now this lens, you can see, has a focal length of around 200 millimeters, so it's definitely not a wide angle lens, even though I can already say this one is designed for a bigger sensor size, so the difference is not that extreme as you might think at first. Let's go into cross-section view, and we can see that this lens is composed of only 4 groups. The first and the last are a singlet, the second and the third are a doublet, and the aperture is located right in the middle. And you can probably agree that this design looks rather symmetric. And the design type here is called the Double-Gauss lens, which is a lens design that has been around for more than 100 years and is still used as a design basis for some prime lenses today. You can actually look at the Wikipedia page of the Double-Gauss design, where you will find many examples of different variations on this design that span over a century of design history. Now I will again activate the ray fan option, increase the number of rays quite a lot in preparation for a 3D fan, which I want to demonstrate. And ignoring the field of view that this lens is designed for, I will add some additional ray fans up to an angle of 25 degrees. I will also activate the RMS focus again. And when we zoom in, what we can see is that for the inner field angles, there is some additional positive back focus, so the best focus location indicated here with the 2D fan moves further back. And then for the largest angle, 25 degrees, there's suddenly a very sharp opposite movement. So the best focus here would be far inward all of a sudden. But now this is where the 2D ray fan really is a problem. Now let me switch to the 3D fan. And we can see that suddenly the picture has changed completely. So while for the inner angles there was not much of a difference, now for this 25-degree angle, all of a sudden it also is a positive back focus compared to the center. And at first glance you might think there's an error, because clearly this passes the smallest focus and widens again towards the best focus location. But that is where the 2D, not only the 2D fan, but also the 2D side view will fool you. Let me remove these additional angles and just reduce to the single angle so that it is marked in edit mode. And when I now pan out into the 3D view around the focus spot, what we can see is that the rays in the plane that we looked at before, which is the sagittal plane, they will focus somewhere over here, but the rays perpendicular, the tangential plane, would have a focus even further back. So actually with a 3D fan, this indeed is on average the best focus location. And this effect here is one of the primary aberrations of lenses, which is called astigmatism, that you have a different focus position in the different planes of the lens. Now this example is definitely quite extreme. The lens is definitely not designed for an angle of 25 degrees, but I think actually 12 degrees should be the correct number. But still, I showed this because it's a nice and obvious example why there can be a significant difference, or a difference at all, in the RMS focus between using a 2D ray fan in a single plane and a full 3D ray fan. And again, back to default view, moving on to another lens. I want to go back to a wide angle system again, but this time even more extreme with an actual fisheye lens. Now, when I switch, notice the comparison in size of the systems overall. So the fisheye is a little bit smaller, but not that much smaller, particularly when comparing the first element. However, the focal length of this lens is just under 2 millimeters, so there's actually a factor of 100 between the focal length of the prime lens I've shown before and this fisheye lens. Also, if you look at the individual elements, you can see there's a huge discrepancy between the first element and the back group over here, which is a lot smaller and a lot more compact. Now I will again add a ray fan with quite a large number of rays to visualize the maximum angle that we can trace here. Again, upscaling the input beam, and with a limitation that I explained before with my current generation of the initial beam, I can trace up to an angle of just over 80 degrees for this fisheye lens without any issues. Above that, it quickly fails at the moment. According to the patent, this lens should actually render an image up to 98.5 degrees even. So very, very large field of view. As I said, I cannot do it with the current implementation of this sequential ray tracer, but it will be something to try in video number 3 of this series, where I will set up this lens with the Cycles render engine. Now, as I said, the focal length is very small, just under 2 millimeters, and the image circle formed according to the patent is around 9 millimeters, so accounting for the entire 98.5 degrees field of view. So comparing to modern image sensors, that would be slightly more than a half-inch sensor type. Now with the wide angle lens before, I mentioned that that lens, so a sort of normal lens, not a fisheye lens, would have a distortion type that is called f tan theta. So the height of the spot on the image is proportional to the focal length times the tangents of the angle. Now, this lens does not follow that relationship at all. Instead, it's closer to a so-called f theta projection. So the position on the image sensor is proportional to the angle directly and not the tangents of the angle. We can visualize this again, zooming into the image plane a bit by creating multiple ray fans up to 80 degrees. I will stop down the beam here because there are some aberrations for the system, and increase the number of rays a little, which will take a little while to compute now. And then we can look at some vertex positions. So obviously for the on-axis beam, the image height is 0. Then for 20 degrees, we have 0.7 roughly. For the 40-degree beam, we have, selecting the right one, we have roughly 1.4. So about twice that. That's okay. But for 40 degrees, the tan theta relationship wouldn't yet change this so dramatically. But for the 60-degree beam, we can see 2.3. So it's actually a little more than 3 times the value of 20 degrees. So this should be 2.1 and not 2.3. However, the ratio of tangents of 60 degrees and 20 degrees would be 4.75. So this is very close to a ratio of 3. And in an f tan theta system, it should be almost 5. So clearly we have a large deviation. And you can also see the 80-degree beams roughly follows the same relationship. We can check it. So it is about 3.3. If it was an ideal f theta without any distortion relative to that, we would expect roughly 2.8, so it doesn't quite follow f theta law. However, the ratio of the tangents should be a factor of 15. So taking that into account, the image height here should not be 3.3, but rather 11. So that is quite a big difference. And so we can confirm that this lens system really renders close to an f theta relationship. Now, as for the wide angle before, just as a quick word, it is again impractical to trace the focus with a 3D ray fan, because here the ratio of the initial beam size relative to the beam that actually reaches the sensor is even bigger than for the wide angle lens shown previously. Right, I'm gonna have to delete everything again to get the operator back. This would actually have been a good opportunity to use the reset performance critical settings feature. However, here we are. I will reduce the number of rays again. Oops, wrong field. I will delete the additional angles, make this a bit quicker. And I will increase the stop size to its nominal value again. And now we can allow some larger number of rays again. What we do see here in this 2D view is that the outer rays of the ray fan have some residual aberrations to the inner rays. So it looks like there would be a pretty good focus spot here if we discarded a few rays on the outside. And indeed, if I stop down the lens by 10%, still a few aberrated rays. 0.8, now it looks like there is a rather clean focus generated, whatever that means, and the RMS focus would indeed place it there. Now, here's a bit of a discrepancy between the zmx file and the patent itself. So I've looked up the patent of this lens online, and between the focus or the nominal image plane indicated in the zmx file and the description in the patent, there is a 50 micrometer offset. And if I apply this 50 micrometer offset, then this places the image plane pretty much exactly where we'd get the RMS focus for this 2D beam. However, with the aperture wide open, the RMS focus 2D and 3D as well, actually, even though this is difficult to trace here, I've tried it separately, would place the focus further back, so a bit more consistent with the zmx file. Now, it's not completely surprising that the zmx file is a little bit different, because the person who transferred the information from the patent into zmx might have refocused the lens for a different blend of angles or wavelengths or whatever choice was made, so a difference is not unusual. I have no further reference for this lens at this time to compare any of this and to comment further on the discrepancies. However, this is something I noticed, that stopping down the lens a little bit makes the focus location on axis very consistent to the patent. However, I should also notice that in that case, the F number given for the system does no longer match, which it does for this full stop diameter. So that is a discrepancy that cancels out my other observation. Now, there's another interesting property of this lens, which is how it achieves this F theta relationship to begin with. And that property lies in the second lens, which the first surface of the second lens is flat, so no curvature at all. And the second surface is actually a parabola. So this lens is an example of a lens using aspheric surfaces. Surfaces are not sections of a sphere. All other surfaces of this lens, of all the other lenses, they are spherical. And also the two lenses that I've shown before, so the Double-Gauss and the wide-angle lens, they are both completely spherical. All surfaces are spherical. Alright, so on the topic of aspheric surfaces, I would like to move on to the next designs. And now I specifically want to move into the category of mobile lenses, i.e. lenses used in smartphones or similar devices. They use multiple aspheric surfaces and in some cases even very complex aspheric surfaces where you can very, very clearly see the deviation from a spherical shape, even more so than for the case of the parabola that we have seen in this fisheye design. So before I actually load the file, again, take note of the overall size of the fisheye lens and its small focal length of 2 millimeters. So in comparison, the first mobile design is a lot smaller overall, as you would expect. I mean, you all know how small the lenses in your smartphones are. However, the focal length at 3.33 millimeters is actually bigger than for the fisheye lens. So again, you can see that size and focal length can be very, very different in comparison for different lens designs. All right, let's take a closer look in the cross-section model. And we can see that this design is only composed of 2 singlet lenses and an aperture that is in front of the first lens. Now, only 2 lenses is quite uncommon. Modern mobile lenses rather have something like 4 or 5 elements and maybe an additional filter at the back. But this design is from the year 2003, and on lensdesigns.com it's also labeled as an early mobile lens design, which would make sense considering that smartphones aren't actually that old. Now, if I add a ray fan, we can again try and check the image properties. So by design, according to the patent, it should perform out to approximately 35 degrees, or well, it's designed to be used for image sensor with corners at 35 degrees. And we can see at just over 30 degrees, a little bit of vignetting starts to set in, which then would gradually fall off up to very large angles, something like 53 degrees. where it's ultimately vignetted. But as I said, according to design, it should be approximately 35 degrees total field of view for the sensor diagonal. Now, this lens is worth inspecting a little closer for two purposes. First, cross-checking that the implementation of aspheric surfaces, so the sequential ray tracing, is actually correct, and also understanding a little bit more about how lenses are typically specified and the role of paraxial calculations in this. Because if for this on-axis beam at 0 degree angle, I zoom in, it again looks like the focus is not really chosen very well. So I've not activated the RMS focus option here, which would place the spot approximately in this location, which looks a lot better. Instead, this image plane comes directly from the zmx file, as it's specified there. And in the zmx file, there's a distance of 1.828 millimeters from the central vertex of the last lens to the image plane. And if we look at the actual patent now, here you can see this lens, the example image in the patent, and we scroll through this patent a bit up to the list of coefficients, so which you can find on this page. Here it lists all the surface radii, the distances, refractive indices, and all the aspheric coefficient for the four surfaces. So the first thing I've done is to double check that there isn't actually any mistake, and indeed I didn't find one, so the zmx file did indeed correctly copy all of these parameters, and also the refractive index is used correctly. And here it also very explicitly specifies this back focal length of 1.828 millimeters as it is entered in the zmx file. So everything seems to be correct up to this point in the zmx file. So we might want to cross-check, is there something wrong with my implementation? One value that we can look at here is the effective focal length, which is cited as 3.33 millimeters in the patent. And OptiCore also gives a result of 3.33 from the paraxial focal length calculation. So that is one aspect that is consistent. Now, to do a further cross-check, I have also built this lens in the free version of WinLens, a software that I've shown previously in my older videos, because it's an optical design software of which there's a free version, and I've set up the lens according to the patent specification in here. Now, the first lens looks a little bit different because it actually doesn't cut off the surface just beyond the initial stop size as it should, but it keeps rendering it out to higher distances. So it looks a little bit different, but other than that, it's the same. And if we look at the surface table here, there is the back focal length indicated in this field. And this is calculated automatically, so I cannot edit this value, as you can see when I double click. And it's rounded here, 1.83, only shows 2 decimals, unfortunately, but it gives the same value. And in the lens drawing, if we zoom in, we can see that its spot, so its focus location, also doesn't seem to be quite perfect. Now I can manually offset this. I will choose 50 micrometers, and this places a dashed line at my new image surface, which looks to be in a much better location. Can compare the same here in Blender, so in OptiCore I can also apply this offset of 50 micrometers, and again it ends up in a good location. So this would confirm that the implementation here is actually correct, or at least it's consistent with a completely independent optical design software that's been around for much longer. So then, if OptiCore is consistent with another lens design software and also everything is consistent with the specifications given in the patterned, then why doesn't the specified back focal length appear to be the optimum image location? And the reason for that is, again, paraxial calculation. So the paraxial approximation effectively is the approximation for rays that are really, really close to the optical axis. So you would do a ray tracing for a ray that is only offset by a very, very small amount. And then that gives you an approximation for something like the focal length or the back focus distance. So for this calculation, everything like aspheric coefficients or conical constants are ignored. It's just taking into account the base radius of the surface. And yeah, because very close to the center, there is not a lot of curvature. The distances of the individual surface points, the intersection points, is not very far displaced from the central vertex. This is an approximation, and usually you would say that for an optical system that is very well corrected, where all rays focus in one point, then if all rays focus in one point, logically you would think that also the rays close to the optical axis would focus in the same point, and so this paraxial approximation should be valid for the lens. However, then we have cases like this, where if we just take the back focal length from this paraxial computations, it doesn't quite fit when considering the entire ray fan. And we can now cross-check this. I will increase the number of rays a little. And now I will, just to show what's happening, I will stop down the lens, zoom in again, and as I keep stopping down, you can now see that this apparent focus location keeps shifting further and further back until indeed this paraxial focus location seems to be actually the correct focus. So it's not completely invalid. It comes from paraxial calculation, and that's why it's consistent between the patterned and also an optical design software like WinLens, which by default would also calculate the focus location this way before optimization with real ray tracing. And in this case, the zmx file that someone has constructed from the pattern was not explicitly refocused to take this into account, but just has kept the paraxial focus distance. And that's how we can see that in this case we would need some offset to get the real ray traced best focus. On the topic of mobile lenses, I very briefly want to show a second design. So before I've mentioned that this early design with only 2 elements is rather untypical for modern lens designs, which are a bit more complex. And so I want to show one example of those, how that looks like. So this is from a newer patent, I think somewhere around the year 2013. And this now is composed of 4 lens elements, 1 flat filter, and still the aperture is at the front of the first surface. And here we can now see that the 4th lens really deviates from spherical shape. The back 2 surfaces are very complex, and there is an inversion in the direction, so you can no longer classify it explicitly as either concave or convex. The polynomial terms really dominate here. Other than that, if we look at a ray fan, this lens is designed pretty similar for a similar field of view of around 30-35 degrees. When we increase the angle, we can see we're still vignetting free up to this point. And again, some vignetting at the lens edges starts to take place around 35 degrees. And then for this lens, there is a really rapid fall off at around 38 degrees or just over 38 degrees, it's already fully vignetted. And now for a last example of a working system, I want to again show a very different type of optical system, and that is that of a reflective telescope. Just slightly larger actually than the mobile lens, this specific zmx file, because it's a scaled down system. And what you can see here is two mirrors, one primary concave mirror and a secondary convex mirror, and the aperture is defined at the location of the primary mirror, which is why in this view it is drawn to intersect the mirror, which is of course not really very physically correct, but that's how optically the system is defined. And this specific type of setup here is called a Cassegrain mirror. So the primary mirror is parabolic and the secondary mirror is hyperbolic. When adding a ray fan in edit mode, we can see that the ray fan first hits the primary mirror, is reflected off it, hits the secondary mirror, and then forms a very, very nice focus spot on axis with a really, really low RMS spot size. And also the focus location in the zmx file is already really, really good for this design. So this type of system with reflective surfaces can also work, although this is a good point to talk about some limitations that there currently still are. So first of all, what you will notice is that the rays originating here at the center close to the optical axis, they should be blocked by the secondary mirror. So the secondary mirror should act as a kind of secondary aperture with an inner blocking rather than an outer blocking radius. However, you can see that the rays just pass through the secondary mirror and are not affected by it. So this is something that I have not yet implemented, that there is additional check in case of system with reflective components if anything is obstructing the beam, and here that is just ignored. And the second aspect is that the primary mirror should have a hole at the center to let the rays pass. So this is also something that explicitly has to be somehow checked, because that's not apparent from the zmx file itself, because optical design is not necessarily identical to mechanical design, and therefore things like these are not very obviously indicated in such a file. And for implementation of this, one would have to explicitly separate these cases. So while the secondary mirror is in the way of the first, of the initial beam, it should be interpreted as an obstruction and block the beam, while beyond the secondary mirror, you could think that, okay, the software might detect the primary mirror also as an obstacle and obstruct the rays, but in this case, it should be handled differently and a central hole should be generated. So this maybe is obvious for a simple lens like this, but for a more complex telescope with more than two mirrors, it's something that may need additional consideration. I am not fully sure yet. I haven't implemented this, as I said, but this is something that needs more work. However, as you can see, the optical focus is indeed generated correctly. The geometry is imported correctly, so this type of system would be usable. A second type of limitation at the moment that would concern telescopes in many cases is that presently I have not yet implemented what is called coordinate breaks in other design software, which means basically that there is a rotation of the optical axis at some point. So this Cassegrain design is a linear rotationally symmetric system where both mirrors share the same optical axis. A counterexample would be, for example, a Newtonian telescope, where there's a primary mirror, which is also typically parabolic, and the secondary mirror would be a flat mirror that is rotated at 45-degree angles so that the outgoing rays would be deflected to the side, and the eyepiece would be located somewhere at the side. And this is something that at the moment OptiCore does not yet handle, so be aware when you're trying to load this kind of lens system that the system may not be imported correctly. In case of a Newtonian system where the fold mirror is flat, that really wouldn't matter much. You'd get the focus position here, so not where it really should be, but still the ray tracing would work correctly and indicate a good focus spot size. However, there are also fully off-axis systems, so-called Schiefspiegler systems, where this would no longer work, because really you'd have to ray trace some off-axis segment of the mirror and not something revolved around the central optical axis. So in those cases, the optical design would really fail and it might not be obvious. Okay, so as the very last example, I now want to look at another category of import error that cannot be immediately obvious. And that is an issue with import of the material of the lenses. For this, I have again a zmx file from a mobile lens design, at which we can look at in cross-section. And from the point of the geometry that you can see here, there's actually no issue at all. So what you see here, without the ray fan being added, is imported completely correctly. All the surface radii, aspheric coefficients, they're all correct. The shapes are correct. So up to this point, everything is absolutely fine. And when I now add a ray fan with a few rays, we see something that I've also demonstrated previously, which is that the nominal image surface indicated in the zmx file does not seem to be a good approximation of where the best focus really is. And given the example that I've showed earlier, that should not surprise anyone, because there might be a difference between the paraxial ray tracing and the full real ray tracing. However, if we do the same sort of inspection for this lens by stopping down, we can see that actually the focus gets even worse. So it doesn't seem like the paraxial back focus is a good match to this image location that is indicated in the zmx file. So yeah, obviously for this lens, that is not the issue. And I've already said it in the introduction, the issue here is the import of the material properties, so the refractive index of each of these elements. Now, why is that? So these files come a lot from patents, and in the patents we have looked at one example earlier of the early mobile lens, and we have looked at this table. Refractive index may be specified by single value at the D wavelength typically, and the corresponding Abbe number for the dispersion. Now, the other way to specify a glass in a zmx file is not using a custom dataset like this, but explicitly specifying the name of a commercially available material from some glass manufacturer or some other material manufacturer, or a scientific source for materials. Yeah, could be different ones, but yeah, either custom dataset like this or using an explicit material specification. Now, using an explicit material specification is actually best, because then you can look up a more precise data curve for the refractive index as a function of wavelength, and thus get a better ray tracing result for polychromatic ray fans, which means considering full white light spectrum, for example, and not just a single wavelength, which is what is actually happening in the sequential ray tracing as shown here. And in a zmx file, if I load the zmx file for this specific lens, then it looks like this here. So there is a line called glass, and there it says E48R. And this E48R is actually a material from a company called Xeon. So their material is then called Xeonex E48R, which you can see here in this column. So we can indeed on the company website find a data sheet. Now in OptiCore, what is needed to actually load this information would be that I have an implementation of a catalog, so a file with all this data. I can't just read it from the PDF document like I can as a human. Maybe in the future there will be AI tools to assist with that, but at the moment I don't have anything like that in my implementation. So I would need a database where to look up this specific material. I have included a few databases from big glass manufacturers, which contains their catalog that they publish on their website of their current product range, and maybe some obsolete glasses that became obsolete a short while ago. But some glasses may be missing. For example, old glasses that have been obsolete for a really, really long time may be present in zmx files for very old designs. Or this is an example of a plastic material used often in mobile phone lenses. This is also not included in my database. So there can be some cases where there is a missing material. And what happens in those cases is that if I cannot resolve a material name, I will just assume refractive index of 1.5 as a standard value, which is bound to be wrong. But if you don't want the ray tracing to fail entirely, then that's what you got to do. And if you encounter a case like this and you're wondering if there is such a mistake, then go to the system console in Blender and you will see that it outputs some errors. So in this case, it indeed did not identify the glass E48R. And also for the second and third lens, polycarbonate is also not included in my lists. So this is something that happens at the moment that you need to watch out for when you think that the focus rendered by the sequential ray tracing is incorrect. In the future, I'm planning to implement different databases. So other people have done work on collecting refractive index information for many materials. There is a site called refractiveindex.info. You can find that online. And if you want to transfer a design like this to cycles and render it with cycles correctly, then you could look up refractive index data on that website, include that in your cycles shaders, and everything would be perfectly fine. Just for OptiCore and its internal sequential ray tracer, that currently does not work.